Welcome back. This is video 2 from section 5.7. Alright, so we've learned that complex zeros occur in pairs and so do irrational zeros. So let's see. We're also going to use what we learned about the fundamental theorem of algebra to work this as well. We're going to kind of put all this together in a new way. We're going to actually use the zeros to write a polynomial function. So we're going to write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1, and 3 and 2 plus square root of 5 is zeros. Alright, so we know there's at least 2 zeros, but remember irrational numbers bring their conjugate pair with them. So technically there's 3 zeros. So for every zero there's going to be a factor in the form of x minus k, where k is one of the zeros. Alright, because the coefficients are rational and 2 plus square root of 5 is a 0, 2 minus square root of 5 must also be a 0 by the irrational conjugates theorem. Use the 3 zeros and the factor theorem to write f of x as a product of the 3 factors. So we're going to write f of x in factored form. So f of x equals x minus 3 times x minus the whole quantity 2 plus square root of 5 times x minus the whole quantity 2 minus square root of 5. Alright, now if we regroup the last two here, we do a little bit of regrouping, we're going to see that these can be written in the form of the factored form of difference of two squares. So what we're going to do is we're going to distribute the minuses and then see if we can regroup a little. So we're going to rewrite this as x minus 2 minus square root of 5, x minus 2 plus square root of 5. Okay, so when we do that, we have x minus 2 minus the square root of 5. We can go ahead and group the x minus 2 together. Over here, we have x minus 2 and then plus square root of 5, and putting the parentheses there doesn't change anything, but it helps us visually to see what's going on. We've got a term here, x minus 2 minus another term, square root of 5, x minus 2 plus square root of 5. This is the factored form of a difference of two squares if our first base is x minus 2 and if our second base is square root of 5. So you don't have to do this. You could just distribute the minuses and multiply and just keep doing the repeated distributive property. But this actually, if you can get used to using this little method, can save you some time. So because these two are in the factored form of difference of two squares, we can work backwards and write this. We'll have our x minus 3, and then we'll have times, and then we'll have x minus 2 squared minus square root of 5 squared. Well, square root of 5 squared is just 5. So we've got x minus 2 squared and then minus 5, difference of two squares, but remember this was square root of 5 times square root of 5. Alright, now that made it getting this far a little easier. You certainly don't have to do it this way because guess what? Now you're going to have to multiply the x minus 2 times x minus 2, so you're still going to have to do some foiling distributive property stuff along the way. So expanding the binomial just means FOIL x minus 2 times x minus 2. So you're going to get x squared minus 4x plus 4. And then you've got your minus 5. So we're going to simplify that. So let's see. 4 minus 5 is negative 1. So we've got x squared minus 4x minus 1. Now we're going to do the whole repeated distributive property thing anyway when we do x minus 3 times x squared minus 4x minus 1. So that's going to give us x cubed minus 4x squared minus x, distributing the x. Now let's go back and distribute the minus 3 times x squared gives us minus 3x squared. Negative 3x times negative 4x gives us plus 12x. Negative 3 times negative 1 gives us plus 3. And so let's combine some terms. And we get x cubed minus 7x squared plus 11x plus 3. So that is our polynomial of least degree that has x minus 3 and both 2 plus square root of 5 and then the bonus 2 minus square root of 5 as zeros. Okay. Descartes' rule of signs is a way for us to know whether or not we have any positive real zeros, whether or not we have any negative real zeros, and how many we think that there should be of each kind. And also it lets us know how many imaginary zeros we should have. All right. Now, when you have a function like f of x equals an x to the n plus an minus 1 to the xn minus 1 plus all the way down to a2x squared plus a1x plus a0, remember we know there's going to be a total of n zeros as long as we count double zeros twice, triple zeros 3 times, and so on. So we know the total number that we should have. Okay? Descartes' rule of signs is going to let us know the number of positive real zeros and the number of negative real zeros, or at least lets us know like a set of possible values for the number of these zeros. So the number of positive real zeros of f is equal to the number of changes in sign of the coefficients of f of x, or is less than this by an even number. And the reason you have to subtract off even numbers like minus 2, minus 4, minus 6 is because imaginary zeros always occur in conjugate pairs. So there's no reason to subtract off an odd number because you're never going to have an odd number of imaginary zeros. Okay, the number of negative real zeros of f is equal to the number of changes in sign of the coefficients of f of negative x, or is less than this by an even number. And again, because the sign changes can either represent a negative real zero or they could represent an imaginary zero that's faking you out, and those always occur in conjugate pairs. So let's look at this in practice. All right, we're going to determine the possible number of positive real zeros, negative real zeros, and imaginary zeros for f of x equals x to the 6th minus 2x to the 5th plus 3x to the 4th minus 10x cubed minus 6x squared minus 8x minus 8. So the total number of zeros has to be 6, but we're going to see how different possible combinations of positive, negative, and imaginary that make up those 6 zeros. So the first thing we do is we look at f of x and we count the number of sign changes for f of x, and that'll get us going as far as positive real zeros. Now, the coefficient of x to the 6th is understood to be 1. So we go from positive 1 to negative 2, and that represents a sign change. Then we go from negative 2 to positive 3, that represents another sign change. Positive 3 to negative 10, another sign change. Negative 10 to negative 6, not a sign change. Negative 6 to negative 8, not a sign change. Negative 8 to negative 8, not a sign change. So the coefficients in f of x have 3 sign changes. So f has 3 or 1 positive real zeros. So the largest number of positive real zeros it could have is 3. The smallest number is 1. So one thing that's nice is that tells you it definitely has a positive real zero. So that can be helpful, just knowing that. And again, the reason you subtract off 2 is because those 3 sign changes could represent 3 positive real zeros, or they could represent 1 positive real zero and 2 imaginary zeros faking us out, okay? Making us think that they're positive real zeros because of making a sign change. All right, now we're going to do the same thing with f of negative x. So first thing we have to do is plug in negative x and evaluate. So we get f of negative x equals negative x to the 6th power minus 2 times negative x to the 5th power plus 3 times negative x to the 4th power minus 10 times negative x to the 3rd power minus 6 times negative x to the 2nd power minus 8 times negative x and then minus 8. So let's simplify here. Negative 1 to the 6th power is going to be positive 1. X to the 6th is x to the 6th. Negative 1 to the 5th power is negative 1 times negative 2 gives us plus 2. And then we have our x to the 5th. Negative 1 to the 4th power is just 1. And then x to the 4th is x to the 4th. So we have plus 3x to the 4th. Negative 1 to the 3rd power is negative 1 times negative 10 gives us plus 10, and then our x cubed. Negative 1 squared is positive 1, and then we have our x squared, so we still have minus 6x squared. And then negative 8 times negative x is going to give us plus 8x minus 8. Okay, now you can think through like I just did every time you simplify for an f of negative x when you do that evaluation. Or if you look, the signs are the same as they were in f of x whenever you have an even degree. Okay, so for the term with an exponent of 6 and 4 and 2, you have the same signs as you did originally. We have x to the 6th plus 3x to the 4th and minus 6x squared. For the terms with the odd degree for the exponent there, an odd number for the exponent, so the 5, 3, and the 1, you end up with a sign change. So whereas we had minus 2x to the 5th in f of x, we have plus 2x to the 5th. Whereas we had minus 10x cubed in f of x, for f of negative x, we have plus 10x cubed. Whereas we had negative 8x in f of x, in f of negative x, we have plus 8x. So where the sign changes are going to occur just by evaluating f of negative x is going to be wherever you have an odd power of your variable. Okay, and so that's just a shortcut way to be able to do that. All right, so now we need to count the sign changes as we go from term to term for f of negative x. All right, we go from positive 1 to positive 2, there's no sign change. Positive 2 to positive 3, no sign change. Positive 3 to positive 10, no sign change. Positive 10 to negative 6, there is a sign change. Negative 6 to positive 8, there is a sign change. Positive 8 to negative 8, once again, there's a sign change. So the coefficients of f of negative x have 3 sign changes, so f has 3 or 1 negative real zeros. Again, you just subtract by 2. And you stop at 1, just in case you're wondering, because if you do 1 minus 2, you would end up with negative 1, and you can't have negative 1 of something as an amount, okay, when you're counting how many objects there are. Okay, so we know there's a total of 6 zeros, remember, because it's a 6-degree polynomial. So no matter how these things combine together, they have to add up to 6. So the easiest way to do this is to make a table. And you're going to have the first column be positive real zeros, the second column be negative real zeros. Imaginary zeros we're going to have to calculate. And then over here we're going to have total zeros. The total zeros, this column here, you can fill in ahead of time. It is the degree of the polynomial, so it's 6. And the values you fill in the row have to add up to 6. All right, there were 3 sign changes for f of x, and so there are at most 3 positive real zeros. The same situation for negative real zeros. F of negative x had 3 sign changes. So in this case, if there's 3 positive real, 3 negative real, those add up to 6, leaving us 0 for imaginary. Now, remember, you have to subtract 2. Let's go to get all your possible cases. So let's continue with the case that there's 3 positive real zeros. We could match that up with the possibility of there just being 1 negative 0. 3 plus 1 is 4. We need a total of 6. So that gives us 2 to be imaginary. All right. Let's consider the opposite case, where there's 1 positive real 0, but there's still 3 negative real zeros. Well, that would leave us with 2 potential zeros left over, so there's going to be 2 imaginaries, and that adds up to 6 zeros. Or we could have the case where there's just 1 positive real, 1 negative real, so that's 2. 6 minus 2 is 4. So then in that case, there would be 4 imaginary zeros, and those add up to 6. Okay, so the whole thing is considering every possible combination of the possible number of positive real and the possible number of negative real. You consider the total, and then you subtract to get the number of imaginary zeros for each case. This takes some practice, and so you're going to get a chance to practice this well. Okay, guys, that's it for this lesson. So do your problems to try on your own. That's a critical step in this learning process. So make sure you do those and make sure you bring them to class next time. We will go over them and then get you started on your rounds. Okay, have a great day. I'll see you soon.